Now let's take a look at some basic circuit analysis for which it is incredibly useful to use a water analogy. Electrons flow very, very much like water. Like water, electrons can't be compressed together. You can't shove a bunch of electrons into something. They'll just repel each other and go out. In fact, and one electron in means one electron has to come out the other end. So electrons very much like water, and we're going to see that here in these analogies. Now, first of all, we need to get this assumption right that in all circuits, ideal wires are assumed to have resistance 0 ohms. Although they don't really have 0 ohms, typical wire might have like a hundredth or a tenth of an ohm if it's not a very good wire. But we're going to assume for the purposes of this lecture that these wires have 0 ohms of resistance. Now let's talk about how resistances combine. First of all, in series circuits, and we're going to start off with some intuitive understanding of how water flows, and then see if we can apply it to how charge flows. So my question to you is this. Let's take a look at right over here, part A. Which has more resistance to water flow, A or B? Look at these two setups. So the difference is this. Let me just explain what this means. So I've got a pump here, and that's creating a pressure difference between the top and the bottom. So let me just go ahead and draw that in there. This is high pressure. That's P for pressure. And this is low pressure. Again, I'm using those high and low abbreviations. And in fact, we could just even call this zero pressure. Zero pressure. You can set zero pressure wherever you want. I'm going to set it right there. And what we have are these pipes right here are frictionless. This part right here is considered frictionless right there. They're very wide pipes, and we're going to say there's no friction whatsoever. These parts right there, though, that is filled with gravel, and those do have significant friction. So I want to ask you, and here's two situations. We've got one situation A, there's a narrow gravel-filled pipe, followed by a wide gravel-filled pipe. And then for choice B, we've got a narrow pipe, a wide pipe, and another pipe right there. My question to you is, which has more resistance to water flow, A or B? Go ahead and take your guess right there, and we'll see what happens. Now, this is similar to the idea of longer tubes having more resistance. If you've got more gravel-filled pipes that you've got to push against, it is true that B will have more resistance to water flow. So, by analogy, which do you think has more electrical resistance? So let's explain what we got right here. This is our cell right here. That's the cell or battery. And it serves as our power source, sometimes called voltage source or a source of EMF. Which of these do you think has more electrical resistance? Choice A right here has got an 8 ohm and a 3 ohm resistor in series. Choice B has an 8 ohm, a 3 ohm, and a 5 ohm in series. Now the first thing you might notice here is that the width of these gravel-filled pipes here do correspond to the amount of resistance. This is a narrow pipe. It's got more resistance than this wider pipe, which has got less resistance, and the middle-sized pipe has got a middle amount of resistance. So, but let's just ask this, A or B, which has more electrical resistance? Well, you're probably guessing that it is B that has more electrical resistance, and that is in fact correct. Now, we have to understand what total resistance is. Total resistance, we are going to say, is resistance felt and or experienced by the power supply or source of EMF or voltage source. Now, of course, you know, what do I mean by felt? If you took an ohm meter and put it in the place of this power supply right there, just put an ohm meter there instead of that battery, then you would be measuring the resistance felt by that power supply. Now in series, it's very, very easy to figure out. In series, R equivalent is simply the equivalent resistance to all these resistors is just, you add them up. R1 plus R2 plus R3 plus ... Now, that does look a lot like capacitors in parallel, but this is resistors in series. And it does make sense, the more of these gravel-filled pipes that you got to get through, the tougher it is to get through them. Now, let's take a look at what is R total for circuit A right here. What's the R total for this circuit? Well, if you've been following along, you're going to guess, well, 8 ohms plus 3 ohms is just 11 ohms. What is it for circuit B? Probably guessed by now that it's 8 plus 3 plus 5 is 16 ohms. That's easy.